In this video, I want to talk about the subgroups of a cyclic group. I want to start by proving that every subgroup of a cyclic group is cyclic. Let's let G, generated by A, be a cyclic group and H be any subgroup. So I want to prove that H has to be cyclic. So we know G has a generator of A, so what we need to find is a generator for H, such that everything in H are powers of this new element, let's say B. The idea being we need to find the generator for this subgroup H and then show that every element of H is some power of this generator. Since H is a subgroup of G, we know that every element of H is some power of A. So the generator we're searching for is one of the powers of A. So the question is, which one of these powers is it going to be? We might naturally think that it's going to be the lowest one, the lowest positive power. But how do we go about proving that? Let's let m be the smallest positive integer such that a to the m power is in H. So this is the smallest positive power of our group generator that is in the subgroup. Let's let a to the t power be any element of H. And so I need to show that this is a power of a to the m. Using the division algorithm, I can write t is equal to mq plus r, where r is greater than or equal to 0 and less than m. This then gives me that a to the t power is the same thing as a to the mq plus r. Using properties of exponents, I can break this up as a to the mq times a to the r. I can then solve this for a to the r power to get a to the r is equal to a to the m raised to the negative q times a to the t. However, we know a to the m is in H, therefore a to the m to the negative q is still in H. We know a to the t is in H. So therefore, a to the r must belong to H. Since it is a subgroup, it is closed under our group operation. However, we know r is less than m, and m was the smallest positive integer such that a to the m was in H. This only works if r is equal to 0. So since r is equal to 0, I have that t is equal to mq. So every element in H is some power of a to the m. Let's do a couple of examples of working with these cyclic subgroups. Let's consider the group Z15, and we want the subgroup generated by 10. So what does this group look like? Well, we have 10. Z15 is an additive subgroup, so we need 10 plus 10 is 20, which in Z15 would be 5. 5 plus 10 would be 15 or 0, so this would be the entire subgroup. Next, let's consider the group S6 and the subgroup generated by the cycle 1642. Well, this group would contain that element. If we square it, 1642 composed with 1642, we would have that 1 goes to 6 and 6 goes to 4, so 1 goes to 4. 4 goes to 2 and 2 goes to 1, so 4 goes to 1. 2 goes to 1 and 1 goes to 6, so 2 goes to 6. And then 6 goes to 4 and 4 goes to 2. So I would also have the element 1426. I would then need to cube this, so we'll do 1426 composed with 1642. 1 goes to 6 and 6 goes to 2, so 1 goes to 2. 2 goes to 1 and 1 goes to 4, so 2 goes to 4. 4 goes to 2 and 2 goes to 6, so 4 goes to 6. And then 6 goes to 4 and 4 goes to 1. So we need to include that element, 1, 2, 4, 6. We still haven't reached the identity, so now let's raise it to the 4th power, so 1, 2, 4, 6 composed with 1642. 1 goes to 6 and 6 goes to 1, so 1 goes to 1. 2 goes to 1 and 1 goes to 2, so 2 goes to 2. 4 goes to 2 and 2 goes to 4, so 4 goes to 4. And then 6 goes to 4 and 4 goes to 6, so 4 goes to 6. So this would be my identity element. So here is the subgroup generated by the element 1642.